All right, so today we are going over similar polygons and proportionality. Proportions you've seen before, now to one we're going to go over again slightly and add a little bit to it, but similar polygons. So we're going to start with similar polygons, 6.1. So similar polygons, well, what are they? Well, similar polygons are two polygons are similar if their corresponding angles are congruent and their corresponding sides are proportional. And remember, congruent means equal, and sides are proportional, which means that the scaling between them, and if you think about it, scale models are all built on proportionality. Basically, if one side is half as big as another side, then all the sides have to be half as big as the other sides that they correspond with. And remember, corresponding means they match up. If you remember, we did that when we did congruent triangles. Corresponding angles, corresponding sides, and we had to prove things with that. And we'll get into those a little bit later with similarity. All right, so corresponding similar polygons. Sides are proportional, angles are congruent. So the angles don't change, but the sides do. They change size. So here's an example of this. You have this quadrilateral ABCD and quadrilateral EFGH, and we see that angle A is congruent to angle E, B is congruent to F, C is congruent to G, and D is congruent to H. And you see that by the amount of tick marks on there. And what we said is they are similar because they are the same shape. Their sides are scale factors, basically, we're saying them, and their angles are congruent. And we get what we call a similarity statement. If you remember, we had a congruent statement, and the only difference between a congruent statement and a similarity statement is the congruent statement has an equal sign under the squiggly line. So we have here ABCD is similar, that's what the little squiggly line means, to EFGH. So if you think about congruency, what does congruency mean? It means similar and equal because it's those two together. So similar, same shape, different sizes, all right, versus congruency is same size, same shape. And I know we go through congruency first instead of similarity, but if you think about it, congruency is just a special type of similarity, whereas they are both congruent, they are both similar and equal. So if you think of it that way, it's pretty cool how it rolls back into each other. All right, congruence is similar and equal. I just said that. Corresponding angles are congruent, as we said. Corresponding sides have the same scale factor. The ratio of the sides are the same. So if like one side's 10 and its corresponding side is 5, and then you have one corresponding side of another one is 12, then we know that the corresponding side to the second one has to be 6. 10 to 5, 12 to 6. And they all have that same ratio, 2 to 1, 3 to 2, however. And it can be any type of fraction, but it is going to be a fraction. So it's not going to just be like a number 5. It'll be like 5 to 1 or 1 to 5. And it does depend on your perspective, because if we go big to small, your fraction better be bigger than 1. So like your bigger number better be on the numerator. Versus if we go small to big, the smaller number needs to be in the numerator. So keep that in the back of your mind as we're doing this. All right, so here's an example. We have triangle RST is similar to triangle XYZ. So that's given. We're telling you they are similar. And I give you here, we have RST, XYZ. We say RS is 25, ST is 30, RT is 20, and respectively XY is 15, YZ is 18, and XZ is 12. And we want to list all corresponding angles. So if we do that, you just say which angles are congruent to which angles, and we've done that before. We say, all right, so we just match it. R, first letter in the first triangle, R is matched first letter in the second triangle, which is X. So we say angle R is congruent to angle X. Then we go to the next one. Angle S is congruent to angle Y. And then we can say the third one, angle T is congruent to angle Z. And if you want to mark it, R, X, S, Y, and T and Z. So we can mark them on there. And then we want to check the ratio of corresponding sides. So let's just write down which sides are corresponding, right? So if we look at it, we know that RT corresponds with, RT corresponds with XZ. And we also want to know that there's RS, and that corresponds with XY. And then our third one, which is ST, and that corresponds with YZ. And what I just did there is actually I just did part C, which is the statement of proportionality. Because what I'm doing is a statement of proportionality. Unlike a similarity statement where we're saying this object is similar to this object, statement of proportionality sets up every proportion among all corresponding sides. So RT to XY, or XZ, RS to XY, and ST to YZ. And so we can check the ratios. So if we go back to what we're looking at, RS to XY, well, that's 25 over 15. And if you reduce that, that gives me 5 over 3. We do the same thing to ST over XZ. That's 30 over 18. Divide them all by 6, that's 5 over 3. And if you do RT to XZ, that's 20 over 12. Divide all those by 4, you get 5 over 3. So you'll notice that each one of these ratios all reduces to 5 over 3, 5 over 3, 5 over 3. So since the ratios are the same as in the reducing, and the angles are congruent, as we know, the similarity statement, is going to be holding true. So write a statement of proportionality. So we did it. We did RT to XZ, RS to XY, ST, YZ. And again, it doesn't matter the order of these three as long as you say this is equal to this, equal to this. And as you see that, they're all equal. Now, scale factor. Well, the scale factor is basically, guys, what do you notice about all three of these ratios? They all reduce to the same amount. Well, guys, that number, that 5 over 3, that's my scale factor. So there's my number. That's my scale factor. And that's going from the first triangle to the second triangle. So default answer is whatever the first one listed to the second one listed. All right. Unless we tell you bigger to small, small to big. So in this case, 5/3. All right. So that's my scale factor. So that what all these ratios reduce to, that's my scale factor. And you'll notice every single one of them the same. If one of them was not, then they wouldn't be similar. All right. So here's the first theorem of this section. Perimeter of similar polygons. Right? And it tells me if two polygons are similar, then the ratio of the perimeters is equal to the scale factor. Basically saying if they are similar, then the ratio, the perimeters are also going to have that same ratio. The ratio between the sides is going to be the same as the ratio to the perimeters. And so I give us an example here. ABCD, or ABC here, is similar to DEF. And we see that AC corresponds to DF, AB corresponds to DE, and CB corresponds to FE. And you'll notice that what's my scale factor between them all? It's 3:1 from ABC to DEF. So let's think about this. If we just went AB to DE, and we did that from AC to DF, and did the same thing from BC to EF, and we put the numbers to it, we should still say the same scale factor. So we got 12 to 4. Oops, sorry. Let's make sure it's in order. 15 to 5, 12 to 4, and 9 to 3. And we see they all end up 3/1, 3/1, 3/1. So let's do the perimeters of each of them, right? So perimeter of triangle ABC is 12 plus 15 plus 9. And so think about 12 plus 15 is 27, plus 9 is 36. Whereas the perimeter of triangle DEF, that's equal to 5 plus 4 plus 3, which is 12. And so we see that 36 over 12 is also 3:1. Thus, the theorem is true. All right. Same scale factor as the ratio of the sides is the same scale factor as the ratio between the perimeters. 1. That works out every time. So if you know the perimeters, you can figure out the scale factor to the sides and vice versa. All right, so now we get into something we've done before slightly. When we did this last semester, we did proving triangles were congruent. So we said all corresponding sides, all corresponding angles were congruent. And we ended up with those 5 nice ones. Angle, angle, side, angle, side, angle, side, angle, side, 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 and hypotenuse leg. And you remember we had a couple that weren't actual theorems. That was side, side, angle. That's a no-no. It's the bad word. And then there was angle, angle, angle. And we didn't use that one because that didn't prove anything about congruency. Now, SSA still doesn't work. That's not going to work for this one. However, angle, angle, angle. We don't use angle, angle, angle. We just use 2 angles. It does work for similarity, because if you think about it, two angles of one triangle are congruent to two angles of another triangle. The third angles have to be congruent. So we don't need all three angles. We just need two of them. So if we can prove two angles of one triangle are congruent to two angles of another triangle, then the triangles have to be similar. Could they be congruent? Possibly. But we know they are similar. So I'll give you an example here, JKL and XYZ. K and L are congruent to YZ respectively. And since they are congruent, then the triangles are similar. So be on the lookout. That does happen. So angle, double A, does work here. We don't even need the third angles. You can prove them, but we don't need to. So that's one way of doing it. The second way is an old friend of ours, and that's side, side, side. Now, instead of saying all the sides are congruent, proportional, we say all the sides are proportional. So if the corresponding angle side lengths of two triangles are proportional, then the two triangles are similar. So if you just do what we did beforehand, which was show every side, do the statement of proportionality you see here, if AB over RS, BC over ST, AC over RT, if they all hold the same ratio, same scale factor, then the triangles have to be similar. So instead of telling you they're similar and then knowing that this ratio is going to hold true, if we can prove the ratio true, we can now prove the triangles are similar. And kind of the easiest way to do this, guys, because they're not going to be just lined up perfectly for you all the time, is when you're comparing sides, compare the longest side of one triangle to the longest side of the other triangle. Compare the shortest side to the shortest side, and whatever the middle side is to the middle side. That's the easiest way to think about it. Long to long, short to short. If you keep that in mind, you cannot go wrong when comparing. You're going to be tempted to compare one side that's shared between two triangles, because we've had that before. And when you do that, you're going to get in trouble, because you're going to have two sides that are congruent, and then you're thinking, I got to go congruency. No, we're not in the congruency realm anymore. We're in similarity. So longest side to longest side, shortest side to shortest side. All right, and then another one we've seen before, side angle side. All right, side angle side is basically the same thing. One angle of one triangle congruent to one angle of another triangle. And it's the in-between angle. So remember, it's the angle that's between the two sides. And then we say the two sides are similar. They hold the same ratio. Then the two triangles are congruent. So I give an example here, triangles XYZ and M and P. If X and M are congruent respectively, and then we have ZX and XY compared to MP and MN respectively, see ZX over PM, XY over MN. If those ratios hold true and X and M are congruent, then the two triangles are congruent as well. All right. So right now there's three ways. There's only three here, not the five we did for congruency. There's three for similarity. Side angle side, side side side, and then angle angle. Right. So angle side or angle side angle does not work here. Will not help us, because angle. But if you think about it, angle side is covered by angle, and same thing with angle side angle. We don't need them. Double A takes care of those already. So we knock those off. And then HL was only for right triangles, and we get that anyway with side angle side, or angle at this point. So we'll be good at that point. And right triangles are a lot easier. So I give an example here, and I say, show triangle XZW is similar to triangle YZX. All right. XZW is similar to YZX. And I give you all the sides of every triangle. Now, what you have to realize is we're not trying to prove anything congruent here, but we are trying to prove two triangles are similar. Now, think about this. XZW, that is this triangle right here, XZW. It's this one here in blue, right? And then YZX is YZX. That's the one here in green. So my big triangle of WXY, we're not needing it. We're not doing anything with it. But we are trying to prove these two triangles are similar. So let's think about this. Angle, not going to quite, we don't know the angle. You know, one angle, 90 degrees, but that's not helping us. All right. However, sides can. So we want to try to prove they are similar. So let's think about this. XZ is going to correspond with YZ. So let's think about XZ is 12 here. XZ has to correspond with YZ. If we do the other one, ZW corresponds with ZX. ZW over ZX. And then the last one is XW corresponds with Y-axis. And I know this can get confusing because all of a sudden we're going X's, Z's, and X's, and Y's, and W's. They're all shared and both for the triangles, but you got to keep them straight. Blue triangle, two green triangles. So we're doing blue triangle on top and green triangle on the bottom. If we keep that straight, we should be good. So let's think about this. XZ on the blue triangle is 12 versus YZ on the green triangle. YZ on that one is 9. Go with ZW. ZW on the blue triangle is 16, whereas ZX on the green triangle is 12. And then we go back to the blue triangle. We say XW is 20, and then XY is 15. And you'll notice I'm comparing what I have written down in my ratios. So it's always a good idea to write your ratios first before you start plugging in numbers. Because again, you're tempted to go, ooh, 12 to 12. I know that one. That's an easy one. But that's not right because that's not the comparative sides. They're not the corresponding sides in this one. All right, and at this point, guys, all we have to do is say, what are my ratios? 12 and 9, both divisible by 3. That's a 4 over 3. 16 over 12, divided by 4. It's 4 over 3. 20 over 15, divided by 5. That's 4 over 3. Since they all have the same ratio, are the two triangles similar? Yes. And we can say yes by side, side, side. And then we're done at that point. There's my reasoning. I showed my work, and there's my reasoning. Yes, by side, side, side. All right. So the last thing here, and I don't have it written out, is proportions. And we're going to deal with proportions real quick. We know proportions, we've seen proportions, and we just got to be more familiar with proportions. Are two fractions that equal to each other. We saw the proportionality theorem. So if you think about it, A over B equals C over D, right? That's our basic proportion. That is a proportion. And when we solve proportions, what do? Well, to solve proportions, we do cross multiplication. We cross multiply. So again, we'll go back to our A over B equals C over D, and we can cross multiply. So A times D equals B times C. So we can say A times D equals B times C. Right? We all should be able to remember that. Right? So we could have something, for example, 5 over x equals 3 over 12. And we want to solve for x. What is 5 over x equal to 3 over 12? And so we can cross multiply, and we get 5 times 12 equals 3 times x. And we get 60 equals 3x. So x here, in this case, equals 20. And that would be my answer. Now, there is a special case that comes up in proportions, and they're called geometric means. And I'm just kind of giving you the hint because you might see this on a SAT type problem. Geometric mean. Now, don't think of geometric mean as like arithmetic mean, which would be take the average. Geometric mean is a little bit different. Geometric mean is set up to where you end up with something like this, where the numerator and the denominator in one of the fractions, so one in each, are the same value. So you see here we have A over x equals x over b. So it's nothing special. We still solve it the exact same way we did in normal proportions. Just now, what do we have to deal with? Well, now it's x squared equals a times b. And then we'd have to solve using square roots. So you have to be prepared for those. Just be aware that you are going to see this. And I'll give you a very good example here. Like 4 over x equals x over 9. An easy one to do. All right, we cross multiply. We get x squared equals 4 times 9, which we all know is 36. And then when we solve this, remember you have to take the square root of both sides. And so we get x equals. Now remember, when we take the square root of both sides of an equal sign, it's always plus minus square root of that number. So in this case, it's plus or minus 6. So there's actually two different answers here. 2 x's, 2 answers. So x can be positive or negative 6. And if you plug it back in, you'll see it works your ratio. All right. Hopefully that covers proportions. You've seen it before. And the geometric mean is slightly new to you, but again, we still solve it the exact same way. So similar triangles, similar polygons, guys, corresponding sides are proportional, angles are congruent. When you're doing the triangles, you got angle, side, 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 and side, angle, side. And to solve the ratios and stuff for missing parts, proportionalities. And I'll see you guys next class.